So in this last video, we're going to take a look at a solid solution. So let's say somebody presents an analysis where the sulfur content is listed as 53.07, and this will be in weight percent. And let's say the iron content is 47.02, and the arsenic has a weight percent of 0.19. No copper is detected or reported, at least, but there's a little bit of antimony, and it comes in at 0.31 weight percent. So what kind of mineral is this? Would it be a pyrite or bornite? Well, with no copper, you might guess that pyrite is a likely suspect, but let's look at the molecular weight molecular proportions and then see if it fits into this iron, arsenic, antimony solid solution, where we're going to have 2 sulfur atoms for every 1 cation. So the iron, arsenic, antimony should, if it sums to 1, then we should have a total of 2 sulfurs. So the mole proportion, we're going to skip some steps because we already showed how to do these in a previous video. So the mole proportions we would get by taking all of these and dividing them by their molecular weights, which are again shown here. And the values for sulfur would be 1.655. Iron would be 0.842, and then arsenic is 0.0025, and then by coincidence, antimony is also 0025. And these things together would sum to about 2.502. And we're going to convert these into a mole fraction. To get them into a mole fraction, we're going to renormalize by this sum here. So all of these will be divided by 2.502. When we do that, for sulfur, we get 0.661. And then for iron, 0.336. And then 0.001 each for arsenic and antimony. So all of these are going to sum to 1. And take a look at this. Sulfur is, again, about 2/3 of the total atoms, a little bit shy of that. So maybe there's some defect structures here, or there's a problem with the analysis. But this analysis that I picked up out of a journal article is coming pretty close to what we would expect for an ideal case of about 2 sulfur atoms for every 3 atoms total, or 2/3. So if we have if we have pyrite, then that means all of the cations here should sum to 1. So let's just take the sum of these fellows here. And if we do that, those are going to sum to 0.3385. And so we can renormalize by dividing all of these by 0.3385. If we do that for iron, we get 0.994, not a 6, that is a 0. For arsenic, if we divide out 0.001 by 3385, we get 0.003. And then, of course, we're going to get the same thing for antimony, since it rounded off to about the same value as arsenic. So that means in our our precise formula, not the ideal formula, the ideal formula for the solid solution would be iron and arsenic and antimony, and then we'd have a total of 1 of those for every 2 sulfur atoms. But the precise formula would be iron with a subscript of 0.994, and then arsenic with a subscript of 0.003, and then antimony with a similar subscript of 003. And I've run out of room, but we should have a sulfur, we don't have bornite, we have pyrites. I'm going to rewrite this. Let's erase the chalkboard. Our precise formula is iron 0.994, arsenic 0.003, antimony 0.003, and then sulfur 2. So that general formula of iron, arsenic, and antimony for a pyrite that has a little bit of solid solution of these 2 atoms would be a precise formula here for the particular analysis that we started